So what I wanted to tell you a little bit about is this Center for Biomedical Discovery and why this is so important to our practice. And this is the visual identity that we have that the artists rendered for us, and which I thought was really creative. And you can see it's a silhouette of a person. We have various renditions of this, and superimposed on it is a roadmap. And the concept is to convey a roadmap to health, or the roadmap of disease, or understanding the complexity of health and disease, on how fragile we are as human beings, and how complicated being healthy is, and how complicated disease can be, and understanding and navigating through these maps. And so I wanted to give you a vignette here of what do bacteria found on the Easter Islands, and so you probably recognize this idol here, which is about 8 feet tall on the Easter Islands, and a Mayo Clinic cancer patient. What do they have in common? There's not an obvious link between these. But what it turns out is that investigators, not from Mayo, but this was in the 1960s, found a type of bacteria on this island out in the Pacific that had properties of killing other things around it. So it's an antifungal, antibacterial agent that these bacteria secrete. And what was so remarkable about it is that it can be used as an agent to prevent fibrosis, or to kill cancer cells, or to prevent inflammatory responses that we all can be prone to. And so people knew that they had this agent that they called rapamycin. So you've heard mycin on the ends of antibiotics, right? Erythromycin and so forth. And Rapa is actually the native name for the island. They didn't call it the Easter Islands, they called it the island of Rapa. And so rapamycin. And it turns out that Mayo investigators then, 30 years later, defined what this drug was, the structure of it, and the pathways in our cells that this drug affects. And therefore, knowing this structure, they could devise and design a series of analogs, they're called Rapalogs, that can be used to treat cancers, inflammation. They can coat stents on it, if any of you have had stents put in, that will prevent fibrotic lesions from forming. And so, and performed clinical trials that now this is a integral drug that is used in probably half of the different clinical divisions at Mayo Clinic. So this was an example then of these little creepy crawly things that were identified by other scientists on this somewhat obscure island, secreting an agent that we could then utilize and understand to treat patients for a variety of ailments. And so that is kind of the mantra that we have for the Discovery Center, of that you must understand what you're trying to treat. So if you came with a disease, or if your daughter came to Mayo with a disease, you wouldn't feel terribly comfortable if she was dealing with a physician that says, I'm going to prescribe this. We have no idea what the drug does or how it does it, but it's the best we got. And so you wouldn't, I would find that a bit unsettling, right? You wouldn't feel that good about it. And so the idea is that if you're going to repair an automobile, you have to know how the engine works. Likewise, if you're going to treat a tumor or a plaque, you have to understand the molecular and cellular basis by which these diseases occur. And so that is an important part of this discovery, translation, application axis that we have here at Mayo, or the DTA. So I'm kind of in charge of overseeing the D part for discovery. And so along these lines, we organized this center, and we have some money from the dean, executive dean for research, that we're grateful for, into 3 central areas. And so we didn't organize them into areas by organs. We didn't say, okay, we're going to have a brain platform, we're going to have a liver platform, we're going to have a lung platform. We organized them into processes that cause disease, that all of us have to deal with throughout our lives, and particularly as we age. What are they? Well, one is metabolism. So understanding how we use energy, how we store energy, how we misstore energy and might become obese and diabetic. It's a huge health risk. I'll get into that in a little bit. That's one of our platforms. And metabolism can affect pretty much every organ of the body, from the brain to the liver to the pancreas, kidneys, so forth. Cancer and cell aging, which is perhaps more familiar to you. Almost every tissue and organ in the body can become cancerous, and it's a huge problem. We'll talk about that a little bit. And then immunity and fibrosis. So our immune systems are key. The problem is a lot of them are on a hair trigger, and they see things and treat them as invaders that necessarily shouldn't be so. And so we have autoimmune diseases and inflammation and so forth, and fibrosis. So I'll talk about these a little bit. But let's talk a little bit about the discovery science that's going on in obesity. And so many of you might have heard, we're essentially in the middle of an obesity epidemic right now, as far as Western cultures go, whether it be Western, Eastern Europe, or North America, South America, and so forth. And it turns out that half of us in the United States are going to be clinically obese in the next 15 years. 50% of us, and that doesn't mean slightly overweight, that means clinically obese. And so the costs to this are huge as far as diabetes, heart disease, and other issues. And so $66 billion per year is going to be dedicated towards obesity-related diseases, absenteeism, and so forth. So you might imagine that understanding the cellular basis of this disease and why we have this tendency to collect fat, both in our muscles and our guts and our liver, is important for us to know. And so I've included a slide here of a histological section of human fat. And I don't know if any of you have ever seen this before. I find these cells absolutely amazing. So there's a picture here of about 10 different fat cells. And here's a cartoon rendition of one of them. Each cell is this giant fat droplet, a spherical round droplet of fat, just like you have when you fry bacon and have grease in your frying pan, surrounded by the cytoplasm of a cell. Is this a touch-sensitive screen? Yes. Okay, I didn't know that. So look at this fat. You can barely see the cells. All you see are these giant fat droplets, right? And their job is to really twofold. One is to store energy, because when we evolved over the past hundred thousands of years, we weren't sure we were going to have a food source every day, so it's important to store that. Now, in the cultures I talked about, we have ready access to fats and to energy and food. We're not out tilling the soil and doing labor, so we accumulate these. But the amount of energy that is stored, and if anyone's had a grease fire, is quite remarkable, right? Anyone try to fry a turkey by dropping a turkey into a fryolator, right, and have a fire go up? I've seen videos of it. The fire goes up about 20 feet. That is burning, releasing the stored energy that's within these fats, or triglycerides as we call them, and into a fire, for example. We happen to release this energy in a more refined way when we're working, moving, running, and so forth. The problem is, with our sedentary lifestyle, we store these in the fact that we can get large amounts of fat around our waist, and you might have heard about apples and pear-shaped storage. We store fat differently. Our livers can become 50 or 60% fat, rather than the hepatocyte cellular basis that they're supposed to be supporting. And so the end result is that these organs can become inflamed. We can have a lot of white blood cells that accumulate, and they can become diseased. So we do a lot of liver transplantation at the Mayo Clinic at all 3 sites. Up until this year, most of the reasons for liver transplantation has been for hepatitis B and C, and damages, liver cirrhosis from alcohol and so forth. over the next couple of years, the primary reason for liver transplant is due to obesity and a fatty liver. And so the liver can become fatty to fibrotic to cirrhotic to dead, and you need a transplant. So it's a huge problem. I wanted to play, let's see if this plays. I wanted to actually show you a fat cell, a living fat cell that we isolated in the laboratory that has been stimulated to reutilize its stored fat. So here is one fat cell that you see. And anyone recognize what those big oval things are? Those are the fat droplets, right? So you're looking at a single fat cell, and there's maybe 7 or 8 fat droplets in this cell. And we're going to stimulate this cell with an agonist that will cause the cell to utilize its fat droplets. And hopefully what you'll see is that you'll see that those droplets are starting to shrink and disappear. Are they kind of going away? So and this is sped up about 40 times. But what you're seeing is this cell breaking down its fat and utilizing it for energy or releasing it out into the surrounding environment. So wouldn't it be great if we could take a fatty liver and stimulate it to do that, right? And get rid of its fat in a controlled way and not have to transplant people's livers.
Is it kind of like burning the fat?
It's breaking the bonds of the fat, these molecular bonds which have high energy in them, and breaking them from a tri down to a di down to a mono form. That can be utilized by the mitochondria, which are the structures in cells that utilize energy. So I wanted to give you an example of why I get excited about this kind of stuff and why it's important that we understand the basis of fat and what it can do to us to cause diabetes and organ damage and so forth. Any questions about fat or anything like that? Or it's an important part of our lives, right? Because we eat a lot of fat. The obesity rate in this country skyrocketed in the late 70s when fructose corn syrup was introduced into almost everything that we eat, almost everything. Did you have a question, ma'am? Oh, sorry. Yes, please.
I have read that fat cells never go away. They may shrink, but they're always there.
Yeah, that's well said. And so you might imagine that if this cell had a giant fat droplet, it would be all puffed out, but if it were to utilize its fat and you were to fast for a day or two or a week, that it would certainly shrink, but the cell would still be there.
Ready to go. Expand.
Ready to re-expand, yeah. Yeah, well said. So one of our other platforms, I told you just about our metabolism platform, is the cancer platform. And we're probably most familiar with the threat of cancer. We find it frightening. No one wants to have to deal with that. This is a picture of a melanoma cell that is moving along, and we'll talk about cell movement in a second. So the largest problem that we deal with cancer is the problem that it doesn't stay put, right? So if anyone here has had a cancer, I had melanoma. I have family members that have had breast and GI cancers. As soon as the diagnosis occurs and you hear about it, you ask the physician, what stage is it, right? You want to know, is it stage 1, 2, 3, or 4? And you hope it's stage 1, because if it is, it can be generally removed by a surgeon, not always, or irradiated, or cut out and discarded and thrown away, or put in our giant biobank that we have here that we store thousands of patients' tumors for research. The problem is that tumor cells have a propensity to move. And so this is a movie of human prostate tumor cells that have been isolated from a patient with their consent, of course, and grown on a culture dish, and then added to it a growth factor. And it's looping here. And so what you might get a sense is that they look kind of static at first, but then they round up with time and then start to move along. and they become less interested in each other. They move apart and start to migrate. And so this is just over a period of 10 or 15 minutes that I'm showing this video. Imagine this phenomena if over the course of days or weeks or years, right? And so this prostate tumor could have left the capsule of the prostate and gone into the blood vessels and ended up in the bone marrow, for example, of this patient. And many of the cell lines that we have at Mayo are from patients that did not survive, but their cells live on in the laboratory. Right? It's kind of creepy. I don't know if anyone has read the book on Henrietta Lacks. Amazing. So this was an African-American woman in the early 1950s that had cervical cancer, and the physicians used her samples of cervical cells and grew them in the laboratory without her knowing. So things have changed since then, certainly. But we have, for example, we grow HeLa cells, Henrietta Lacks, HeLa, in our laboratory. And they grow like crazy. And so people have calculated that the volume of cells that were generated from the cervix of Henrietta could fill this building, for example, over the last 50 or some odd years, right? And so the problem is that the cells continue to divide and don't stop. They don't necessarily divide faster, but they don't stop. Like a normal, the cells of your kidney don't know when to stop, right? Your kidney stops at a certain size. These cells continue to divide, and they end up becoming metastatic and invading peripheral tissues, whether it's the brain or the lung or the liver and so forth. So scientists here at Mayo are trying to understand, keeping your tumor stage 1 is kind of the initiative that we call it. Keeping it in its place and preventing it from going elsewhere. Let me give you an example. Here's another picture of a tumor cell. This is a pancreatic tumor cell. And it's on top of a fluorescent substrate. So here's the cell. And so you might ask yourself, well, how do the individual cells leave the tumor and get into the blood vessels? Because the blood vessels are, they're like a straw. How does it? Well, the tumor cells will actually secrete things that will eat away the surrounding capsule of the tumor and eat away a hole and get into the blood vessel or the lymphatics. So what you're looking at is a pancreatic cancer cell that's on top of a fluorescent substrate. And this cell is going to move along, and it's going to leave a black trail wherever it chewed up this matrix by secreting a protein. Let's see if this plays. So there's the cell moving. Can you kind of see it? And do you see it's leaving this black trail of destruction by secreting a protein that is eating away the green gelatin underneath. Now this cell is on top of a glass slide, so it can't eat through glass. But if it were on top of a blood vessel, it could eat through the blood vessel and go in and then shoot off and go to a distant organ. So this process of metastatic invasion, as we call it, of moving, leaving the primary tumor, separating, dispersing, migrating, secreting things that will allow it to eat through obstructive barriers, involves hundreds of different proteins and signaling properties and so forth that we study here at Mayo, and other places do as well.
Do different
Please.
Cancer cells perform this process at different speeds?
I'm not sure if it's a matter of if a melanoma would do it faster than a pancreatic tumor. I think it depends on what the properties of your tumor are. So you may...
Gleason scale?
Yes, so as far as prostate goes, so if you have a bad Gleason scale in which those cells have left the capsule of the prostate, those cells may have signaling cascades that make them move faster or degrade things faster. And so it depends how lucky you are with the characteristics of the tumor. Good question. So these are just some of the interests that we have in regards to understanding the molecular basis of cancer. Any other questions about that? We could talk about cancer forever, right?
Yeah.
Another one of our interests is inflammation and fibrosis of organs. And so many of you are familiar with the immune system and the importance of fighting infection and so forth. The problem is that it can become hypersensitized. And so here's a cover of Time magazine. I included that just to show you how much in the forefront of our society it is. It's called The Secret Killer, Inflammation. Because white cells of your body, they're called T cells or B cells that go through your lymphatics and your blood vessels, will attack things that are infections. The problem is that sometimes they are unable to discriminate between what is self, you, versus what is an invading pathogen. And those things end up causing asthma, arthritis, transplant rejection, right? And so it's a huge problem. And so we have entire departments of immunology here trying to understand the cellular and molecular basis of the immune system, of how it can be aimed like a laser to do good things, like attack a tumor cell. And you might be, immunotherapy is very much in the news right now, and maybe some of you know people who have had immunotherapy, of using the immune cell to attack your tumor. The problem is, how do you get it to it? I mean, the tumor is you, right? It's not an invading thing, so how does the immune system get targeted in a specific way to attack a tumor and not attack you, your organs, your brain, your liver, your lungs? So there's a huge interest in this field right now based on its promise and so forth. There's also a problem with inflammation in that your organs can become fibrotic. Some of you might know people that have had obstructive pulmonary disease, OPD, cirrhotic livers from alcohol abuse, or from infection and so forth. And so I've included an example of some images of lungs and collagen that are secreted by cells that form this dense matrix. So we have collagen in our skin, right? It provides a protective barrier. A lot of movie stars have collagen injected into their faces. As we age, we lose the right kind of collagen that's desirable to have. The problem is that this fibrotic stuff that helps form strength around blood vessels and skin and so forth has no business being in your lungs or being in your liver or your kidneys. All it does is get in the way and kill the other cells. So as we age, we have a tendency to our tissues become fibrotic. Well, what happens during aging? Why do our lung cells produce all this collagen and cause these dense plaques that you can see by X-rays and MRIs? We don't know. We're trying to figure that out. So we have scientists here studying the molecular cellular basis of cells in your lungs, for example, that can cause OPD, or the cells in the liver that can cause cirrhotic livers and so forth. So another basic set of questions that have huge health potentials. We calculated that 40% of the patients that come to Mayo have a problem with their immune system in some way. Another 30 to 40% have a fibroproliferative disorder, meaning making collagen in an organ that it shouldn't be making it. So you combine that, that's more than 60% of our practice would benefit from understanding the biology of just these two processes, right? It's not talking about cancer or metabolic disorders or aging and so forth. So there's a huge incentive for us to understand and discover the basis of these diseases. I wanted to end with a kind of an important story that I'm passionate about, because I happen to know the young woman who is in this hospital bed. Her father's a good friend of mine who works at the Rockefeller University in Manhattan. This is Elena Simon, and she has just recovered, or recovering, this was about 10 years ago, from a liver resection. So she has this lethal form of liver disease called fibrolamellar hepatocellular carcinoma. And it's a weird cancer that occurs in teenagers and young adults. It's generally lethal. She was lucky in that it was localized and they could cut it out, but they don't know if they got all of it. So her father he's a very bright guy, he works at the Rockefeller University, as I mentioned. And as Elena, who was very smart, went through high school, she got interested in working in her dad's lab. And long story short, here's a picture from one of the sections of the Wall Street Journal about 2 years ago of Elena, who's a very pretty young woman. Maybe she was just about to enter college. And there's her dad, Sandy, in her laboratory. And the name of it says, Teen Helped Research Her Own Disease. So they actually identified a gene that was responsible for her cancer. And so they published this high-impact paper in the journal Science with about 5 other people from Sandy's lab. And now this has led to a series of clinical trials that are promising. There have been no treatments for this cancer other than surgical. And so Elena actually researched her own disease and helped come up with therapies that were important in this. This is the paper that was published back a couple years ago, 2014. And she actually went to a science fair, and here she is all dressed up, and you can see that there are these little noodles, all right, what the pool noodles that you swim with, and those are to represent chromosomes that show mutations in the chromosomes. And so she was talking to people at this science fair, explaining the basis of her disease, and she had a high-level audience here with the president. Since then, she and her dad have frequently gone to Capitol Hill to discuss the importance of discovery science and what it can do for us. She also did an internship with Sheryl Sandberg of Facebook, who you might know from, is it Leaning In? Is that the book she wrote? Leaning In, yeah. Very, very smart woman, and now she's a student at Harvard and learning molecular biology and bioinformatics. So what does this have to do? Well, you can see this is an example of how important discovery science is, and a team science. So I'm in charge of a group of liver cancer biologists at Mayo, and together we've organized a set of experts interested in cancer, and we've built this research pyramid. We call it the discovery pyramid. So down at the base here's a picture of me and other cell biologists and immunologists and geneticists who are understanding the basis of cancer and projecting this information to clinician scientists, hepatologists, pathologists, surgeons. Rory is a hepatobiliary surgeon, to oncologists who actually treat the patient, and here's Elena up at the top of the pyramid. And so I'm passionate about this story because I'm personally involved in it, but also the importance of having a wide basis of understanding that can matriculate up to people who get closer to the patient and can eventually treat them. And so I think this is the strength of Mayo and what we do here of trying to understand, translate, and apply. And hopefully you're benefiting from that model.